This is Lecture 11, Somatosensation and the Motor System, and this corresponds to Chapter 11, All Sections.
Okay, starting in Section 1 of Chapter 11, Hierarchy of Movement Control. Quick review of some of the basics. Afferent information is information that's coming from the body to the central nervous system. So this includes somatosensory information from sensory neurons around the body. Afferent information, on the other hand, is information that's moving from the central nervous system to the body, moving out, and that includes motor responses. We've also covered the spinal cord briefly, but just to review, this connects the somatosensory system and the motor system. So this afferent information and efferent information, and that's connected sometimes by interneurons or sometimes sensory neurons synapse directly onto motor neurons. There's the posterior tract, which is sensory information, and that forms the posterior root. The anterior tracts are motor and forms the anterior root, and various segments of vertebrae groups are grouped together into 5 different regions. Each of those regions represents a portion of the skin called the dermatome. As well, different layers of the motor cortex and somatosensory cortex are specialized for different functions. So if you look over here, layer 4 of the cortex is for sensory input. Integration happens in layers 1 through 3, and then efferent information is stored or moves through sections 5 through 6. And notice that in the sensory cortex and motor cortex, the layers are organized in a similar fashion. So the main nervous system components that we're going to talk about in movement are just the basic central nervous system, so the cerebrum and this brainstem, which make up the brain, and then the spinal cord. And even simple movements, even the most basic movements, typically involve communication between several systems and regions of the central nervous system. So we'll start with the cerebrum, which again is like the forebrain, or the higher level part of the brain, what we mostly think of as the brain. The cerebrum creates motor sequences, which are sort of packets of motor programs. So individual movements are sort of packaged together and pre-programmed by the brain as a unit, rather than having each individual thing, like to pick up a cup, you don't want to have to think, you don't want the brain to have to organize every single movement that is required to pick up a cup, and so they're kind of packaged as a group. As one motor sequence is being executed, the next sequence is being prepared, so it's sort of on standby. And motor sequences code for kind of simple actions that we do a lot over and over again, such as picking up a glass, putting on your glasses, sitting down in a chair, picking up a book, something like that. The planning and also the initiation of motor sequences takes place in the frontal lobes. So most of the motor activity, or planning and execution, takes place in the frontal lobe, so forward from the central sulcus. There are 3 main sections of the frontal cortex, and each one has a different function in the motor system. So the frontal cortex is used for a lot of different things, but motor function is one of the main things that happens in the frontal cortex. So the prefrontal cortex is the top of the hierarchy. That's kind of the newest part of our brain in evolution. And the prefrontal cortex plans behavior, motor behavior, specifies what the goal is. So if you're going to pick up a cup, the goal is pick up the cup, that the cup gets into my hand. Lesions to the prefrontal cortex cause poor decision making, inappropriate behavior. People with prefrontal cortex lesions act sexually inappropriate, and they know that this behavior is incorrect, but they can't seem to make a different decision. So can't seem to inhibit behaviors that they know are not going to bode well for them. The next region, this purple region, is the premotor cortex, and this receives instructions from the prefrontal cortex and then coordinates the movement between multiple body parts, and lesions predictably cause an inability to coordinate body movements. Finally, there's the primary motor cortex, which integrates this information to produce skilled movements. Lesions to the primary motor cortex cause impaired reaching and grasping movements, impaired talking. The brainstem is also involved in motor activity, so the brainstem is responsible for kind of really basic movement, innate movement that has been part of a species' motor vocabulary for a long time throughout evolution. So the stimulation of a brainstem, for example, in a cat can cause this arching, this back arching that they do when they're angry or scared. Chickens have this specific way that they screech in response to a threat. So survival behaviors are often innate to a species and mediated by the brainstem. And our ability to stimulate the brainstem and get these behaviors, induce these behaviors in animals indicates that the brainstem is in fact involved in complex behaviors. Brainstem kind of has a reputation for being very, very, very basic and really not involved in complex behaviors, but at least in the motor system, this isn't the case. So the brainstem also plays an important role in automatic or relatively automatic and rhythmic movements, such as maintaining posture, walking and swimming. Walking is actually a rather complex motor action that requires rhythm, so it requires the ability to repetitively and smoothly execute motor schemas. Abnormal development of the brainstem can result in cerebral palsy, which is a motor disorder that's characterized by a lack of motor coordination, poor balance, stiff muscles, tremors. People are often in a wheelchair. There are often also issues with sort of the coordination of some higher level cognitive functions that are associated with cerebral palsy, although there are plenty of people with cerebral palsy with normal intelligence or above average intelligence. And if you're interested in cerebral palsy, there's this YouTube comedian named Zach Anner who has cerebral palsy and kind of has a series about his life. He actually makes some workout videos, kind of tongue-in-cheek about his life with cerebral palsy. The spinal cord acts as a relay between the body and the brain, and also has some of its own complex functions. So reflexes are mediated by the spinal cord. For example, the scratch reflex, which is when you scratch a dog's belly and his hind leg starts moving as if he's trying to scratch at the same time. That's actually just a reflex. In people who have spinal cord injuries, depending on where the injury is, how high or low on the spinal cord, it can have different effects. So in somebody with quadriplegia, quad meaning 4, this is a paralysis of all 4 limbs. And this happens due to a higher location of the spinal cord injury. Paraplegia is caused by a lesion or damage slightly lower on the spinal cord, and this is just paralysis of the legs. Section 2, motor system organization. The motor system is very adaptive and versatile in general. The motor cortex in the brain, so when I say motor cortex, I'm typically going to be referring to this primary motor cortex, this strip of cortex right in front of the central sulcus. Researchers have mapped out the motor cortex by stimulating patients during neurosurgery. So if someone is getting neurosurgery and their brain is already exposed, a lot of times researchers will take this opportunity to learn a bit more about the brain, and this is in waking surgeries. So the patient is awake, their brain is exposed, and they'll sort of stimulate different areas of the motor cortex and see what body part moves during that time. The motor cortex has a topographical organization, which, if you remember from before, means a spatial organization of the body that's represented in neural or sensory systems. So for example, in the motor cortex, if you look at this little image on the left here, in the motor cortex, the thumb is near each of the fingers. The fingers are sort of in order on the cortex. What's this associated with the hand and the wrist, elbow, for example. So the body is kind of mapped onto the cortex, and this is also called a homunculus, which means like a little man. So there's like sort of a little man mapped out on the motor cortex. The motor cortex kind of has functional movement categories. So for different areas of the motor cortex, there's different categories such as grasping or climbing or bringing food to the mouth that are encoded in different areas. You can consider it sort of like a vocabulary of movements with different vocabulary groups encoded in different areas. And this can be changed by practicing different things, which would increase their representation on the cortex, or learning new things would create new vocabulary in the motor cortex. The neurons in the motor cortex code for behaviors by increasing their firing rate as well as the frequency, increasing the frequency as well as the duration of the firing rate. So if the primary motor cortex gets a command from the prefrontal cortex that it should grasp a mug very strongly, then the neurons would fire more quickly and also would fire for a longer time, which would code to an increased force of movement, increased grasp. Sometimes we might see neurons in the motor cortex firing even when someone is not moving, and this is coding for planning a movement as well as withholding a movement, so kind of wanting to do a movement but not doing it, inhibiting this. There's still sort of the motor plan is still being activated in the cortex, as well as imagining a movement. So there's a famous study where an individual was in a coma, I think, and they were asked to imagine playing tennis. I'm sorry, they probably weren't in a coma, they were maybe just not able to respond. So I think they had Blockman syndrome, where they weren't able to respond, but they were still conscious, and they were put in a scanner and asked to imagine playing tennis. And the parts of the brain in the motor area that are associated with playing tennis started being activated just by them responding or imagining that they were playing tennis. Motor cortex is plastic. It changes according to learning, and it can change in response to injury. So if one area is injured, other areas can compensate for the function that was affected by that injury. So, for example, if an area that is dedicated to the elbow and shoulder movement is lesioned or cut, then part of the neighboring area can become designated to these functions instead. This only happens if the damaged function is practiced. So the individual who has a damage to the elbow and shoulder part of the brain has to practice moving their elbow and shoulder in order for other parts of the cortex to compensate for those movements and gradually regain functioning. And this is called constraint-induced therapy, which is kind of a forced use of the damaged function in order to regain that function. So motor plans that come from the cortex move down through the spine, through these corticospinal tracts, and these are axons that originate mostly in the motor cortex, extend down through the brainstem. Some of these tracts remain ipsilateral, so on the same side. So if they started in the right hemisphere, they would remain on the right side of the brainstem and the spinal tract, though a couple tracts run contralateral, so to the other side. Contralateral tracts are responsible for contralateral limbs, arms and legs, as well as digits, fingers and toes. Anterior corticospinal tracts move ipsilateral midline muscles, so kind of the core body muscles. And so there are 2 tracts per side that are extending down from the spinal cord, 2 tracks from the right hemisphere, 2 tracks from the left hemisphere, and these synapse with both interneurons in the spinal cord as well as motor neurons. The anterior horn of the spinal cord is topographically organized, so there's kind of a little, sort of like a little homunculus in there too. If you look at the image, you can see that within the anterior horn of the spinal cord, there's the area that's responsible for the fingers, right next to the arm area, which is right by the shoulder area, and then the trunk, or the kind of inside the shoulder. And important to remember that motor neurons are the final pathway for all motor commands. So everything that originates in that prefrontal cortex comes all the way through this system down to motor neurons, which are the final part of the nervous system to execute the motor commands. Motor neurons and the interneurons work together to control both extensor and flexor muscles in the body. So extensor and flexor muscles are sets of muscles that work in opposition to each other. An example would be biceps, which is a flexor muscle, and triceps, which is an extensor muscle. So triceps are in the back of the arm, biceps are in the front of the arm. When you flex your arm, you show your biceps. When you extend your arm, that's using your triceps. And acetylcholine is the neurotransmitter in the body that's acting to connect motor neurons to muscles. So motor neurons are causing the release of acetylcholine into the muscles.